So Claudio spoke of networking to identify common issues between different industries. And I think you will find that you have some issues in common with the exploration of deep space, exploration of the inner planets and the outer planets. So how many of you have heard of JPL, the Jet Propulsion Laboratory? How many of you have heard of NASA? Oh, a little more. Well, it's my great privilege to be part of the only team that will be the first to explore the solar system. The NASA Caltech Jet Propulsion Laboratory is the world's premier research and development center for the robotic, that is unmanned, exploration of the solar system. Indeed, Voyager 1 has now left the solar system and is operating in interstellar space. I act as a deputy to the chief engineer of JPL, as well as serving as the JPL Chief Knowledge Officer, the CKO. I also serve on the board of directors of the 63rd Reliability and Maintainability Symposium, RAMS. Some of you may have attended that. My background is in reliability engineering, including 20 years as a NASA reliability engineer before I joined the JPL office of the chief engineer. So here are some other JPL firsts. The Mariner 2 Venus probe in 1962, for example, was the first successful interplanetary spacecraft. I believe this may be the golden age of space exploration. I'm not about to bore you with describing all 47 current spaceflight missions at JPL, but I'd like to highlight a couple JPL projects. And incidentally, 80% of NASA projects are international partnerships. The Curiosity rover is a mission you've probably heard of. The most recent of 4 rovers, JPL has successfully landed on Mars. I plan to show you a video in a few minutes that will highlight one of the reliability engineering challenges in the design of this mission. The rover is about the size and mass of a small car. It uses nuclear power instead of solar panels because of the latitudes on Mars in which it operates and because of the power demands of the instrument suite, including a laser cannon that samples boulders. JPL's goals include finding if Gale Crater ever had conditions favorable for microbial life. It's already expanded our understanding of Mars's habitability for future human exploration of Mars. Curiosity has already completed its primary 2-year mission, and its operation has been extended indefinitely. Plus, a Mars 2020 rover modeled on Curiosity is in development at JPL. How many of you have heard of the Kepler spacecraft? Oh, I'm surprised. It's a mission that I find particularly interesting for reasons you'll soon understand. So we know that our solar system has planets, including Earth, and we have assumed that it is common for distant stars to have planets circling them. But the JPL Kepler spacecraft has actually imaged new alien worlds. Planets light years away are generally too small for current telescopes to image directly, but Kepler can view planets as they make a transit across their sun and measure the planet's mass and its distance from the sun. It does this by measuring the sun's reduced brightness and the time it takes the planet to make the transit. So interesting science, but the results are quite astonishing. As of 4 weeks ago, it has verified its discovery of 1,284 planets with 99% certainty. And a total of 21 of those planets reside in the habitable zone, meaning that they're the right mass and the right distance for their sun for water to exist in the liquid state. Now, we've learned that organisms living deep in Earth's ocean, where light never reaches, where you have water and energy, you have life. Extrapolating to our Milky Way galaxy, this corresponds to 10 billion planets circling M-class suns like ours and potentially habitable to life. So having personally moved from the field of reliability engineering to the field of knowledge management, I'd like to suggest to you that a threat to the continuing success of your company is your ability to make good use of what you know. In some industries, firms invest more in knowledge-based capital than they do in physical capital, such as equipment and buildings. Yet, knowledge is often treated as if it has little or no value in terms of reuse. Many of you who are reliability engineers had to learn statistics in school. Now you attend conferences like this one, or RAMS, my conference, to learn the latest statistical techniques. Clearly that knowledge still has value to you and you seek to retain it. The Romans used pozzolan concrete to build large structures. Here you see the Pantheon on the left, the Colosseum, and Roman baths. But the formula for concrete was lost for 1,000 years until a textbook was discovered in the year 1414. They built Roman baths from England to Turkey, and then the world forgot how to make large concrete structures. It's even easier for a company to lose the knowledge that is critical to their competitive edge. Key institutional knowledge may be lost unless leadership, the leadership of your company, supports active measures to retain it. Now, I've placed an emphasis on critical knowledge. Not all knowledge is critical to a company continuing to do what it does best. What it does best may be making reliable products, and that's where you come in. JPL makes some of the world's most expensive and most risky products. We make a single unit designed to do the impossible. And if it breaks, we can't send someone to fix it. We can't send someone, a maintenance technician, to Mars. So reliability engineering is critical to JPL. Is engineering knowledge critical to Coca-Cola Company? No. And Coca-Cola makes sugar water. Is marketing knowledge critical to Coca-Cola? I'd say that's their specialty. So what knowledge is critical to JPL to retain and share internally if it's to continue to explore deep space? Well, JPL spacecraft are high unit value, often one of a kind, that must operate with precision in an extremely hostile environment. Deep Impact on the right there traveled 268 million miles, 431 million kilometers at 64,000 miles per hour to hit a small target. Accomplishing that is what I call extreme engineering. Kind of like extreme sport, only it requires a team. So what do I mean by extreme engineering in a reliability sense? When Cassini spacecraft reached Saturn in 2004 after its 7-year cruise, it faced a severe radiation environment for the next dozen years. And the Huygens probe had to descend to the surface of Titan through an atmosphere similar to Earth's primeval soup and land on a beach next to a liquid hydrocarbon lake. So how many of you are in the oil and gas industry? Yeah, some of you. Well, you have to capture and retain the knowledge of how to operate equipment under extremes of heat and pressure. JPL spacecraft face environments unique to deep space. Megarads of radiation, space debris, vacuum and zero gravity, extremes of temperature and thermal cycling, the launch vibration, etc. Our mission-critical failure modes do not tend to be time-dependent. Rather, they are associated with critical events, where the total operating time of the component may be measured in minutes. Or in this case, the total operating life may be a fraction of a second, the time it takes a pyrotechnic pin puller or wire cutter to fire. But all 60 or more pyros must fire in a precise sequence during a Mars entry, descent, and landing. Mars entry, descent, and landing, or EDL. Spacecraft face extreme limitations on mass and volume, as well as on other factors like power and propellant. As complex as a spacecraft and rover design may be, the mission design may be more complex. This graphic depicts the series of steps in achieving entry, descent, and landing for the office desk size, about half the size of that table, Spirit and Opportunity rovers in 2004. The entire process of achieving Mars orbit and descending to a touchdown takes about 9 hours. In the case of the 2012 landing of Mars Science Laboratory, also known as Curiosity, I believe there were actually 76 pyrotechnic devices like pin pullers that had to fire in sequence. The lander had to separate from the cruise stage and then enter at the precise angle of attack so the lander doesn't skip off the atmosphere of Mars or heat too much in the case of a low angle of attack. Then there are events that trigger parachute deployment, heat shield separation, and by the way, separation without recontacting the lander, inflation of the airbags, at least for the 2004 lander, and deployment of spring-loaded wheels and manipulator arms. And because we can't communicate with the lander during EDL, software reliability is a big concern. If it takes 2 years to get to Mars, and let's say operates for 10 years on the Martian surface, you have a total 12-year mission, but 90% of your risk, the risk of mission failure, may lie in the last 7 minutes of EDL, the last 7 minutes prior to touchdown, when most of the events depicted here take place. The 7 minutes of terror. This video highlights some of the technical challenges related to just achieving a landing on Mars. As you watch it, I'd like you to consider two things. First, the reliability engineering challenge in successfully triggering these sequences over the course of 7 minutes after the system has traveled millions of kilometers. And secondly, the impact on JPL as an organization and its Mars exploration program if JPL did not have a Mars mission every 5 years or so. Would we be able to retain the technical knowledge of how to land on Mars?
When people look at it, it looks crazy. That's a very natural thing. Sometimes when we look at it, it looks crazy. It is the result of reasoned engineering thought, but it still looks crazy. From the top of the atmosphere down to the surface, it takes us 7 minutes. It takes 14 minutes or so for the signal from the spacecraft to make it to Earth. That's how far Mars is away from us. So when we first get word that we've touched the top of the atmosphere, the vehicle has been alive or dead on the surface for at least 7 minutes.
Entry, descent, and landing, also known as EDL, is referred to as the 7 minutes of terror because we've got literally 7 minutes to get from the top of the atmosphere to the surface of Mars, going from 13,000 miles an hour to 0 in perfect sequence, perfect choreography, perfect timing, and the computer has to do it all by itself with no help from the ground. If any one thing doesn't work just right, it's game over.
We slam into the atmosphere and develop so much aerodynamic drag. Our heat shield, it heats up and it glows like the surface of the sun. 1,600 degrees.
During entry, the vehicle is not only slowing down violently through the atmosphere, but also we are guiding it like an airplane to be able to land in a very narrow, constrained space. This is one of the biggest challenges that we're facing, and one that we had never attempted on Mars.
Mars is actually really hard to slow down because it has just enough atmosphere that you have to deal with it. Otherwise, it will destroy your spacecraft. On the other hand, it doesn't have enough atmosphere to finish the job. We're still going about 1,000 miles an hour. So at that point, we use a parachute.
The parachute is the largest and strongest supersonic parachute that we've ever built to date. It has to be able to withstand 65,000 pounds of force, even though the parachute itself only weighs about 100 pounds.
When it opens up that fast, it's a neck-snapping 9 Gs.
At that point, we have to get that heat shield off. It's like a big lens cap blocking our view of the ground to the radar. The radar has to take just the right altitude and velocity measurements at just the right time, or the rest of the landing sequence won't work.
This big, huge parachute that we've got, it'll only slow us down to about 200 miles an hour. And that's not slow enough to land. So we have no choice, but we've got to cut it off and then come down in rockets. Once we turn those rocket motors on, if we don't do something, we're just going to smack right back into the parachute. So the first thing we do is make this really radical divert maneuver. We fly off to the side.
Diverting away from the parachute, killing our horizontal velocity and our vertical velocity, getting the rover moving straight up and down so it can look at the surface with its radar and see where we're going to land. And we head straight down to the bottom of a crater, right beside a 6-kilometer high mountain.
We can't get those rocket engines too close to the ground, because if we were to descend propulsively with our engines all the way to the ground, we would essentially create this massive dust cloud. That dust cloud could then go and land on the rover. It could damage mechanisms and it could damage instruments. So the way we solve that problem is by using the sky crane maneuver.
20 meters above the surface, we have to lower the rover below us on a tether that's 21 feet long, and then gently deposit it on its wheels on the surface.
As the rover touches down and is now on the ground, the descent stage is in a collision course with the rover. We must cut the bridle immediately and fly the descent stage to a safe distance from the rover. The design challenge from highly unique missions. These twin rovers are the predecessor to the Curiosity rover you saw in the film. Much smaller and solar panels for power instead of nuclear. We are unable to communicate with the landers during the EDL process, so the entire sequence is conducted autonomously by the lander itself. One reason we decided to launch 2 identical rovers to Mars in 2004 was so that we could land the Spirit rover in the geologically interesting Gusev crater, which offers greater science return opportunities, but in case it crashed on landing in the harsh terrain of the crater, we had the second Opportunity rover in the Meridium Planum, the plains of Meridiani, which resemble
I don't know if you've heard of the Rub al-Khali, the empty quarter on the Arabian Peninsula on Earth. Pretty much rolling sand dunes, fairly flat. That is, by placing opportunity in a mostly flat terrain without many rocks, we could at least have one rover land safely, make it to the surface safely. So the engineers like that location, even if the scientists did not all that much. There is a reliability engineering challenge because you don't really know what conditions you will encounter in an alien environment. But the Mars environment is extremely hostile. The temperature in this conference room is about as warm as it gets on Mars. If you're at the equator and it's noon and it's the Martian summer. But tonight, the temperature may drop 100 degrees Celsius tonight. So, both rovers were designed to last 90 days in a harsh Martian environment. 90 days. However, Spirit lasted for 7 years, and Opportunity is still active after 12 years of Mars exploration, although it has experienced some wear. So, reliability engineering. Mission highlights include finding extra Martian meteorites, such as the heat shield rock, and over 2 years studying Victoria Crater. It survived dust storms and reached Endeavour Crater in 2011. So why do we need a formal program at JPL to capture, retain, and share reliability knowledge and other knowledge related to the design and operation of interplanetary spacecraft? Well, one, our last rover we landed on Mars 4 years ago cost about $2.5 billion. That's more than the gross domestic product of Greenland. The parts and materials in the rover are equivalent to those in a small family sedan, a Mini Cooper. So most of the $2.5 billion was to acquire the knowledge needed to design, build, launch, and operate it. And most of that knowledge can be reused and will be reused in the Mars 2020 rover. And two, some JPL knowledge, how to land on Mars, autonomous spacecraft control, exists nowhere else. I mean, who else lands on Mars? Do you know of another company that does it? I haven't run into one. I mean, who else visits Venus, Saturn, Jupiter, and their moons? So knowledge lost cannot easily be restored. And three, it's not just the cost of restoring lost knowledge, but there is higher risk because the replacement knowledge has not been proven in ground test and in spaceflight. If you no longer had access to Mill Handbook 217, you'd probably find another source for reliability predictions. But it'd be more risky because you're familiar with Mill Handbook 217. You know its strengths and weaknesses. It's the same with landing on Mars. Here is what I call the silver tsunami. NASA today has almost 4 times as much engineers and scientists over the ages 50 as under the age 35. And in comparison, 20 years ago, the two age groups were exactly equal in size. The distribution, as you see on the right, was almost flat instead of the bell curve favoring older workers you see on the left. Many other industries, like the oil and gas industry in the US, also has a large percentage of the workforce nearing retirement age. Why is that important? Well, not all knowledge can be written down. What we call tacit knowledge only exists in people's head. You can't teach someone to ride a bicycle by giving them a bicycle user's manual. But even knowledge that can be captured easily and retained may not be, because an emphasis on knowledge capture, retention, for reuse and sharing is not part of the company's culture. Now, this conference is sponsored by Reliasoft. I mean, does their software help to store and codify reliability knowledge? I think so.
At JPL, we use fault tree analysis, FAMICA, worst case analysis, part stress analysis. We don't make much use of reliability predictions, maybe more life testing, because we don't operate our spacecraft in an office environment. For PSA, we've developed an extensive database of stress factors specific to our parts usage, because the stress factors are deep space stress factors. So like your company, JPL has a distinct way we perform reliability engineering. But if JPL hired a reliability engineer from outside, they wouldn't know that. And over the years, our spacecraft have endured failures due to unexpected failure modes. That is also knowledge we wish to capture and retain for future space missions. You may bring some key reliability knowledge from this conference back to your company to add to its intellectual property. So I wish you to think on whether knowledge developed for a project at your company is being effectively retained for reuse on another project. When someone completes a study, do they just save it on their hard drive, or do they also move it to a repository for others to benefit? Can you encourage them to do so? NASA thrusters. Small rocket engines typically fire continuously until they switch off, or they fire in rapid pulses. Why? Because such thrusters are simpler and more reliable. The Mars Science Laboratory descent stage, also known as the sky crane, which you saw hovering in the film, needed descent thrusters, retro rockets, where you could adjust the output, like the accelerator pedal in a car varies the engine output. Why? Because the sky crane needed to hover, as you saw, off the surface of Mars while it lowered the rover to the ground. The problem was that JPL had not designed a throttleable thruster since the Mars Viking lander, bottom right, that was designed around the year 1970. We had lost the knowledge of how to design throttleable thrusters. Fortunately, we found some retirees from the Viking project. They were still alive. We could interview them, and they were able to help us. What is your risk posture? So what's the risk posture at your company? Why does a senior reliability engineer earn more than a junior reliability engineer? One may earn 50,000 reals while the other earns 40,000 reals. So what is your company getting for the additional 10,000 reals? Both can perform reliability analyses. The junior reliability engineer is likely more familiar with the latest tools. Now, I would argue that the additional 10,000 reals is paying for knowledge. Single string. Yeah, I mean, a company that makes metal grinders for the auto or aerospace industry may have only a single reliability engineer working for the company. Or even with multiple reliability engineers, knowledge capture is not fully redundant. Remaining personnel may not know what they don't know. In the Dark Ages, did they even realize they'd lost the knowledge of structural concrete? Gothic cathedrals were built with stone, rubble, and mortar. They used what they had and didn't know there was a better way. So JPL provides an extreme example of unique key knowledge that can be lost. But your company also has key knowledge that's key to its success, tacit knowledge. You can document procedures for doing reliability prediction, but maybe not knowledge on what problems you should expect. So what can you do, or your company do, to manage critical knowledge more effectively? First, there has to be a commitment to preserving critical knowledge as a valuable resource on the part of senior management. Too often we treat knowledge as if it has no residual value after we first use it. Then, because you can't effectively preserve all knowledge, you need to determine what is really critical to preserve. I think part stress analysis is as much an art as a science, at least in NASA environments, deep space environments, where you have stress factors that are off the charts. And a lead practitioner may be able to offer tips that are not found in a guideline document. But your company probably already conducts activities like seminars to share knowledge, so you need to identify gaps in capturing, retaining, sharing it, and implement activities needed to address those gaps. There are many best practices used in industry. JPL has a lessons learned committee that has met weekly since 1984. There is mentoring of junior employees by senior employees. The US military has long had a practice of filing after-action reports after every training exercise or battle that briefly outlines what they did right and what they did wrong. A pause and learn is a NASA version in which peers, like a set of project managers, can share stories on how they solved a problem, because most management problems are the same between projects. And you can't tell if you're being effective in preserving key knowledge unless you collect data. Like engineers at JPL, you are doing difficult technical work and taking technical risks. So it behooves you to act as a champion and to encourage your coworkers to champion the retention and sharing of knowledge that may be reusable, to make good use of what your company knows. Thank you.